back there. This is George King. He's coming out of Houston to speak to us on casing design and whatnot. He's very accomplished. His resume is impressive. Started in '71, so we got 50 years in the game. Professional engineer in Oklahoma and Texas. In the past, he's worked for Amoco, BP, Rimrock Energy, and Apache Corp. Currently researches and consults on well intervention, fracture-driven interactions, well failures, and unconventional resource completion, stimulations, production, well integrity, and shut-in startup operations. He's here representing Viking today to talk about casing. I'm gonna let him do it.
All right.
Go ahead.
Sounds good.
Hey, Sean.
Thank you all, and of course we had the usual problems with the electronics and computers, but you get to expect that after a while. We've done thousands of these things. All right, what I want to do today is to look at the casing damage that we have seen during and after a frac job. Some of the problems that are out there, some of the things to watch for, the red flags that you can actually see one of these things coming if you ignored some part of the design or some part of the application. So we'll get through this, and I only have 17 slides here out of when I teach this course on a day basis. I have about 400 or 500 slides that I'll go through. So there will be some holes in what I'm presenting today. If you want, I've got business cards up here. If you want the copy of this, which I'm going to allow API to put on to any, use it any way you want. But if you need the full deck on this that has really a lot of the detail that we go into, drop me an email and we'll find a way to transfer the file over to you. When I make a presentation like this, I give the slides away because as we learn, every time I give it, the presentation changes a bit with what we have learned. All right, now, casing damage in offset wells and casing damage in the well you are fracturing are the things that we've been looking at. And so basically, this does not mean the casing has completely failed. This can be as simple as the casing becoming oval from a non-uniform load that's pushing in, and then you can't get a frac plug down the length of the well. And this has happened about 5 to 6%, 10% maybe of the time, and it's more, it happens more frequently in certain areas. And you can trace that one back to one of the 5 factors, and we'll go through those in just a little bit here. And it's the geology. And this comes back to either you're activating a fault, and when that fault moves, there's one rule that we know here: if the earth moves, the pipe loses. That's just it. And it may not collapse completely because many of these movements are fairly slow and they're fairly small, but you don't need but about 6% ovality change before that round pipe is a little bit oval and the frac plug, which has a close clearance on it, is not going to go down, and you're going to lose a couple of fracturing spaces if you don't have an alternative method to be able to get down and to isolate into those zones. Okay, so just remember this one, that one thing here: if the earth moves, the pipe loses. That's the geology side of it. But it's not only faults. Many of these, especially shales, have bedding planes and layers in here, and if those get fluidized, shale will creep. Doesn't happen very fast normally, but if it does, it will start pushing on casing. And when you go back in for refracs on some of these shale wells, you're going to see this. You're going to have a tough time, even after you squeeze the perfs, you're going to have a tough time getting that frac plug down there in some cases. So it's good to run a fingered caliper down there to see what you have beforehand. That saves you a lot of problems. Now, Basin Specific, these are the 5 things. First is geology, bedding, not bedding planes, but bedding planes. I love autocorrect. It's a wonderful thing. You want to kill it every once in a while. All right, and of course you won't catch that if you're doing a check because that's spelled correctly. All right, now, Directional drilling is the next piece here that we look at, and it's generally due to sharp changes in the borehole itself. Somebody is trying to get something back on track a little bit too quickly. You create a wrinkle or a little bit of a buckle in that pipe, and your frac plug is not going beyond that. So these are the things to look for. Well construction, the design, the drilling, and the cement, we'll look at the end. There's a couple of things you can do when you're doing this well construction that will minimize the amount of casing damage that you have. And I'll just give you a little preview here. Use a heavier wall pipe if you're in an area which is prone to some kind of ovoid. This is one thing we found at Viking, is that when you start getting into a light wall pipe, you collapse that a little bit easier, or oval it, not maybe completely collapse. There's also a factor here on cyclic fracture pressuring, and you'll see looking at the bottom hole pressure that if you run 8 or 10 crack jobs along a lateral, you might not see this, but then when you get into the 20, 50, 100, the record is over 200 fracks in a single 30-mile long lateral, that you do cycle that pipe. We'll get into more of that later. And then a little bit on fracture-driven interactions from offsets, and most people call that frac hits. Now, when you are doing this, it's when, generally, if you don't see it by the first 1 to 3 toe stages, it'll be the end of the frac before you see this thing happening, and it'll be near the heel. The common areas are the dog leg areas and dog legs along the lateral, but anywhere in the lateral, usually found above the last frac zone, and it may be 200 to 500 feet down the well towards the heel. When you're fracking way up here, the next time you can't get a plug down there. That's what's happening here, is you are getting deformation. So the design of the casing, they're succeeded by either geological, mechanical, physical, and sometimes corrosion events, but this is more likely erosion events. Now, there's a lot of information on this. I've written papers on this, co-written papers with some very, very sharp people who have looked at fatigue in pipe when you continually cycle that pressure. And that's what's hurting you. Now, and the last thing here is really poor cement support. And I have to go back to this almost every time, because if you have a really good cement in these wells and you do have a smooth well bore, you rarely have problems with this. So it can be a factor. Now, this is just a spider diagram looking at some of the fractures here, and casing deformation starts with, we look at the rock fabric, look at stresses over time, come around here, you look at a lot of these things. Coupling is, it's mostly an API 8 round. About 50% of the wells we do is still API 8 round or modified buttress. All right, if you have a gap in there, that first 40 or 50 joints down, and particularly right under the wellhead, you may see some severe erosion when that sand starts going down through there, because you have to get those boundary planes established, and that's usually about 15, 20 joints down the pipe. Use some premium couplings, especially in that upper section, or put some gap rings in there. That helps. And then you go around, then you go around to some of the other clearances here, the proppant type, all of those things factor in, but this is what we look at when we tear down one of these problems. This is an actual recreation with a finger caliper of what a directional drilling looked like when someone made just a little bit too much correction or hit a ledge or some kind of a problem down in the wellbore. When you've got something like that, if you could find that beforehand, you can run a string mill through there or some other way to clean that up. You virtually eliminate the problems. But if it buckles in that area, if you have distortion in that area, and then cycle it, that's where your deformation is likely going to be, and we tracked that back. I've got SBE and UTEC papers on that. Send me a note, I'll be glad to drop those back to you. Now, dog legs are gonna be worse than you think. I know that most of this time we're reporting a 6 or a 7 degree dog leg over a stand of pipe. But if you look at the continuous fluctuation of that wellbore, you're gonna see a lot more than that, and at Viking, we have seen 25 degree dog legs along a well where only a 10 degree dog leg along the stand was reported. So if you have some drilling problems in there, if you think that you're seeing a possibility of that, please get a fingered caliper. There's other things you can run, but we've had more luck with a fingered caliper, multi-fingered caliper than anything else. What we're seeing is if you've got undulations going through here, dog legs, and you run that pipe, let's say you can get the pipe in there. As you frack, the pressure will be at non-uniform loading points. That is the lead off here on the mechanical side. Now this is exclusive from the geology unless the geology decides to work in the same place that you have the mechanical problem in, then you're probably really gonna have an issue. That's where that red flag comes up. Now, this was paper, and when I do these things, I generally put the SPE, and that's an eyeball test here, and I flunk it. But this is on the slide. You get the original slides. It looks pretty good. Now, this was the dog leg severity reported from just measuring the inclination or azimuth change on a stand. They had a continuous measurement here, and this is what it looked like. So there was a lot of changes down the length of that wellbore that we were not expecting. Just as an industry, we don't expect that, and yet it happens. And basically, when that happens, if you look at the stress, you'll see that it peaks and ebbs just with these touches as it goes through, and if that formation decides to move just a little bit, you got a pipe hole. So that's one of the issues there. If you have any suspicion that you have this type of deal, please run those multi-fingered calipers. Now, this is what happens. If you have 0% ovality, that frac plug will go down the casing. The frac plug in red here, and of course I use a hollow frac plug, in case my perforating guns don't go off, but that's only a 1% chance. Yeah, I've studied that. But as these things start to get more and more oval, you will reach a point where you're touching here and you get into a lot of problems in terms of pushing it down, or you won't be able to do it at all. And if it buckles ovals just enough, when you do that frac, you might land a ball there, but a lot of that erosive sand slurry is going to come by in those small areas that isn't sealed. This is why when you see some of these well failures, you'll see some ovality, but you'll see the casing cut apart right there. And it takes less than 20 minutes to chew a hole through pipe with a sand slurry, particularly on the larger sands, but you can even do it with 100 mesh. These are some other things that I worked on. I've got to work on all kinds of weird stuff when I do the dams that I've been in here. But this will cut the pipe out, and that can be the cause of the failure. Please don't, there's one thing that we see time and time again at Viking. They'll have a problem with it, they can't get the plug down, they'll get it out, and they'll run in with a mill, and they destroy every bit of evidence, and then you do have a broach or a leak in that pipe. So try to take care of it ahead of time, because the remedial actions from this are not big. Now let's look at the pressure. This is bottom hole pressure, actual bottom hole pressure measured during it's not a 15 frac job in this particular one. Notice that it's from about 8,000 peaking at about 14,000. That's a 6,000 PSI cycle, up and back, up and back. And as you do this, you look in here, and what does it do to your pipe? Well, if you're in 5.5, that 6,000 or so PSI cycle is going to give you about a 0.015 to maybe a 0.02 inch. See, that's not much. And you're right, and steel will take that for a while, but after a while, you will fatigue the pipe. You will fatigue the cement within 15 cycles. And you will start cracking the cement. What saves us there is that shale is ductile, and you may even have a little bit of a leak outside the pipe. Some of you have seen this drilling where you drill and you have methane bubbling up around the pipe or some type of gas bubbling up around the pipe for a couple of days and then it quits. That's because the formation has formed around that pipe and resealed it. Okay? There's a lot of things happening here. Mother Nature actually, it's a CYA deal. All right. The bigger the pipe you're using, the bigger the pipe you're using, the more that is going to flex. If you want to prevent this, flexible cement, latex cement, extremely strong cement, and there's some other types of approaches. You can actually do a double if you put another string of pipe in there, which is expensive, but nonetheless that will stop it. But even when it is bounded, you're going to have that pushing out, and it goes from elastic behavior into plastic behavior pretty quickly, and as it does, you're just building up strain in that pipe. This is where the fatigue comes in. There's a Urtech paper that we did on this that used the Wellcat model, and the Wellcat wouldn't even show it until they put a fatigue model in there. And that actually triggered the knowledge of what that's caused by. And this, hey, this was from 2002. This is not new. This is basically a Halliburton shot. And this is pipe, cement pipe inside pipe, cemented up and then pressured up, it cracks the cement in there. So you are going to crack that. If you have an area that is specifically very, very susceptible to this, consider that cement, put a little latex in there, use a harder cement, a stronger cement. But after a while, no matter what you're doing, you're going to destroy and get your microannulus in there. All right, that can be cured by the formation. I'd hate to count on that as my only cover. All right, now fracture-driven interactions. Fracture-driven interactions can be a factor as well. This is frac hits. And there are a lot of things that we look for in a frac hit. A frac hit isn't necessarily bad. It isn't necessarily going to damage your production. In some cases, Haynesville, Bakken, it will improve your production about 50 to 80% of the time. But in some areas like the Woodford, the Niobrara, and the Eagleford, you've got a very high possibility you're going to lose some production. And the reason behind that is water transfer. There's a lot of little factors you go into. I had to cut out a couple of slides here to make the time element work. But if you're fracturing, you've got an old passive well right here and you've got your new well right here, look for the areas of the passive well, the older well, that have been depleted. Take some little bit of diagnostic and some tracers to be able to see this. But don't line your frac direction up, your perfs along your frac direction, don't line those up with the fracture initiation points in the old well. You minimize damage when you do that, offset them a little bit. And there are some areas that are prone to frac hit damage, there are some areas that are not. But these are just a lot of little different things that we get into in what we're seeing. Now, last slide here. Some of the prevention approaches here: smooth out your well bores. Look for the geologic factor here. And bedding planes, we have only found about 3 or 4 places in the world where bedding plane slippage truly makes a difference. Now, one of them is in Argentina in the Vaca Muerta. And in that one, those bedding planes will slip several fraction of an inch, and that can really cause some ovalization there. In other places, they're a suspect, but it hadn't been proven. So those are some issues. And then on that geologic side, look for your faults. And you can play faults by drilling right next to them, but get on the correct side of the fault where the gas is or the oil is versus the one where the water is. But you hold about 500 feet off there, and we have made some very, very good wells. Back when I was with Rimrock Energy in the Bakken, we made some very good wells just playing fractures off to the side and just doing some small fracs and working our way back down, because as that stress is released, those natural fractures within the formation will open up and you've got a better flow path. So there's a lot of little things that you can get into here. Now, thicker wall casing, I mentioned, we have looked at this, and when we have thicker wall casing in a group of wells, we find less deformation in those wells than we find anywhere else. And it's just one step up in most cases. It's like going from the 17 pound up to the 20 pound, and it virtually eliminates the issue that we have. Then premium coupling, and watch the gap in the J section area. That's where those pipes are coming together. If they don't end up touching each other, you've got a little gap. Well, you pump liquid by that with sand in it, you'll create an eddy current. You'll destroy your boundary layers, and it will take 2 or 3 joints before that boundary layer reforms smoothly and you get your flow lines of that flow going straight. You know, it's a bunch of hand-waving arguments. I can actually show you the pictures and the illustrations of the one where the wellhead is almost eaten into, the section below it, the pump below it is almost eaten into, but by the time you get down 3 or 4 joints, it's disappearing. The erosion is disappearing. So those are issues. Look at flexible cement. Look at limiting the number of frac cycle stages frac stage cycles that you get in there. Most people don't want to do that, but we see that when we get into larger and larger amounts of these, all these factors can play together. Sometimes it isn't just one factor that's creating this issue. All right. That's it. If you have any questions, I'd be glad to answer them or try to answer them at this point. Anybody yet?
Has any studies been done, you take 5.5 casing and by the end of a 2.5 mile lateral, you pump 90 million pounds of sand, slick water. Once that sand gets in the horizontal section, there's nothing to support that sand, so you may have 4, 5, 6 pounds per gallon along the bottom of that pipe. What kind of erosion are we getting there?
Okay, we have done that work in the Horn River Basin on wells that I was helping on up there in Canada. And we were using 110 metric tons of 100 mesh followed by 110 metric tons of the 4070 sand. And in some cases, we went way beyond that. We were using 10 to 12 million gallons in each well. And up at the top, we actually, the companies operating in that area, they severed one head completely off while they were pumping. They severed another pipe about 15 feet below the wellhead, but when it got down into the lateral, they ran a multi-finger caliper on several of the wells up there, and the wear was still within the API allowable diameter in terms of the total diameter here. And you just did not see a lot of it. And it's that boundary layer effect as you're pumping. If it's into a smooth boundary layer effect, your sand is concentrated towards the middle, and this is with slick water. Believe it or not, slick water. You don't even have to have gel to do that. And we saw no damage into the lateral until it got to the perforation clusters. And we're used to putting perforation clusters, put 3 or 4 or 10 or 20 perforation clusters in a single frac stage. As that, hydraulically, you can use 1 shot per cluster, or you can use 3 or 4. But as the sand, just the water comes down, we're looking at a clean pad, You can hydraulically break those things down, but when that sand comes down, the first perforation it reaches that has a low stress, that's where the bulk of it is going in. And I've got fiber optic shots that show that one, you know, it had 6 clusters. The first cluster took all of the sand. And so we need a better way to actually divert those. But when you're talking about erosion, we don't see much downhole unless you get to the perforation. It's right under the wellhead or in the wellhead. Question?
Yeah, I got one for you.
Yeah.
Where, during fracs where there's been issues getting subsequent frac plugs down.
Yeah.
So let's assume ovality, right, or whatever that may be. What best practices have you seen to mitigate, okay, now I can't get my plug down. What are the tricks out there, the techniques that operators are doing to continue their operation?
There's been a couple of things, and none of them are foolproof.
Exactly.
There is one school of thought, we've actually done this, and Nexen up in Canada has experimented with. Amoco did it in 1992 in the Val Hall field, in which we didn't use frac plugs. We were in horizontal doing multiple fracs, 8 typical, on a well in the Val Hall field in the chalk. And basically what they would do is force a screen out, and then that last is packed with sand. They'd come in, they wouldn't clean it out, they'd perforate and then hit it with enough rate. They might have lost a little down there, but they weren't opening that previously fracked section, and they'll go. That's pretty rare that people are willing to try that. The other thing is you can go in with inflatable plugs and set below it, because you can get a perforating gun into there, usually on coil tubing. And if you can't pump a plug, it's hard to do a pump down, because you do need that small clearance to be able to get down there.
Right.
But you can go in, set an inflatable, and then pop a couple of those. You're gonna have to drill it out, and that drilling inflatables out, if you can't grab them and pull them out, drilling inflatables with all that stuff that's in them is tough.
Yep.
It's tough, but you might be able to go in and overshot those things. But that's the ones that I see so far, and most of them they're going in, they'll skip a couple, they say, well, we'll come back later. Well, that can hurt or not hurt you depending on what's going on there, because I'll tell you right now, when you put in 50 fracs along a well bore, if you use tracers and then monitor that for about a year, you'll find that 30% of your fracs, 30 to 50% of your fracs are producing 80% of your production. So we're wasting, and every frac stage is about $100,000. So you're wasting maybe half the money on fracturing. If we knew where to put those fracs, and the best tool I can suggest for that is a mud log with a gas meter, gas show. Look for the gas shows along that lateral, because in a lot of this shale, and I've fracked shale wells in 10 basins now, worldwide. A lot of those shales will have gas in part of it, but not in all of it. And it will, if you have if the natural fractures disappear, you don't have any way to get that to flow.
But in later years, some of those non-productive clusters, after the good ones have depleted, might start.
They come on, but it's usually at a low rate. Now, there's a young lady with Apache, then with, I don't know where she is right now, but she wrote a paper looking at over a year's time with the tracers, and it's down into the parts per billion on these tracers now. Drop me a note and I can get you that paper. But what she was seeing was every frac out there contributed. It just all fracs didn't contribute equally. And when you're doing that, you're looking at, man, the bang for the buck. If you're putting more and more of these stages in, I've got a graph of Bakken work, I don't know whether it was published or not, but I got it from the operator, that looked at cumulative production versus number of fracs, and it goes up like this. It had a 365 IP on it, and it just went up. But if you look at cumulative production per frac against the number of fracs, every one of them was going down. So the rate of return on these fracs in huge numbers of fracs is going down, pretty soon you're gonna have to look at how much money am I getting for that versus how much money did I spend on that frac? So it's a little bit more complicated than all of that, but I agree with you, yeah, some of them will come on. And I've got data on that in the larger file, that if you want that file, I'll be glad to send it to you. All right, questions? You see, we really hammered this, yeah, that.
Back to this, eating up.
Yeah.
So how does that work a little bit more?
I don't have a slide with me to show it, but, okay, you've got the inside of the pipe, or the pipe coming down, you've got your API 8 round, or some of the modified buttress threads that still have a gap in there. All right, that flow is coming down like this, but any variance in the diameter is going to cause some swirl, and it'll cause a current like this, and that'll happen in the angular access ports. If you're pumping completely through a wellhead, you have an angular access port, you'll see swirl cutouts. And again, I've got all those pictures in that bigger set of slides. But right there, you're coming in off the ram's head or the goat's head, whatever you want to call this thing, and that flow is just going all over the place. All right, as it goes down, the streamlines get built, you get the boundary effect laid out there, and that boundary gets a little thicker, and it does force all of that proppant into the center of the flow. We've seen that time and time again on some laboratory work that's been done that I do not have pictures of, but I've seen this work. But yeah, and also if you're flowing a well, say 300 or 400 million a day, or let's say 15 million a day, if you have those gaps, you will see erosion on the pipe that looks down into the flow. If you're just seeing it in fracturing, it's the pipe that's looking up into the flow that's coming down. But you'll see it on high rate gas wells, just the opposite side, but the same type of erosion. I've got shots of that as well. I've got a lot of downhole camera stuff to prove this. Okay, question? Yeah.
We continue to see those first three stages on horizontal frac jobs are hard to get into, tight in all basins. You got a thought on why that?
Yeah.
Why that is?
I've actually gotten to play with this thing in the field, in the Horn River Basin. We had right at a 30% failure rate on breaking down toe stages. They put one stage of perforations out there. It was a meter long, but they put one stage of perforations. But think about this one. These are brand new wells. I don't care how long that you circulate the fluid, you're still going to have a lot of debris in that well. Now you go down with a frac job at higher rates, and drilling, you're just pumping a handful of barrels a minute. You go down to okay, and you go down with a frac job, you've got a slurry of sand in there right now. That is the best cleaning flush that you can put down. It's going to clean that pipe out, and all of that debris is going right into the toe stage. So if you want the toe stage to break down, like I say, 30% failure of the toe stages in Horn River until we put 3 perforation clusters in there, and the failure to break down dropped to 7%. Okay? So it's a trash can, and you've got to have enough trash can volume that you're going to be able to get some clean fluid into there to actually exert some pressures. And when you're a mile, a lateral, you're a mile, 2 miles, they've got 3 mile laterals now. Think of this one. How much pressure can you focus on that toe stage if you're losing the pressure due to friction along here? And I don't care how good your friction reducer is, it'll only reduce it about 70%. So you're going to have less pressure to put on a toe stage than you would on a heel stage, simply because you have less pipe eating up, less pipe friction eating up the pressure that you're pushing in for. Basically, that's what we see. Others? Yeah.
Yeah, are you kind of an expert on
casing, I guess? You know, this is
I'm a
the-
jack of all trades and a master of none.
So,
But I look at the whole picture, that's what's different. I know a little bit about it, so what's your question?
so I mean, are you seeing in the last year, say, just overall in the US, more incidents, I guess, with bad pipe in the hole?
We're seeing more incidences, you know, we really first started getting this going, we were putting 4 frac stages in a 3,000 foot long lateral. That was a big deal. All right, that's 2004. 2008, we were putting 8 to 16 frac stages in a 5,000 foot long well. By the time 2010, 11 rolled around, they were putting 20 to 30 frac stages, and it's gone up and up and up. And Apache did one 4 years ago that used 207, I think it's 207 frac stages in a single, I think it was a 10,000 or 12,000 foot long lateral. When you do that, the bend area of the well is experiencing every one of those 200 stages or 100 stages, however many you want to put down there. And so yes, as the laterals got longer and the frac stages got more, and it's typically more about frac stages, and the sand loads went from, well, 1,000 pounds per foot to, well, when we started, it was less than 500 pounds a foot in 2004, 5, 1,000 pounds by 2010. It is averaging over 2,000 pounds a foot now, with some operators experimenting with 3,000 pounds. And I know that one company down in the area there in South Louisiana, they pumped 50 million pounds of sand in one well. I have not been able to follow up to see how that worked, but in any case, we are increasing the cycles, we're increasing the sand load, we're increasing the length, and yes, we are seeing more damage. We're seeing more reports of that.
Do you have any kind of feeling for whether or not that's strictly casing related, because it was bad casing to begin with? The manufacturing process has gone downhill a little bit?
We have, to my knowledge, we have not found but 1 or 2 illustrations of bad casing. Some of this has been geologic, and I think that's one of the more common ones because we're just not looking for it. We're not looking for bedding, plane, slip. We're not looking for things. And the mechanical side is we're getting dog legs and non-uniform loading in more places than we think. And then we've never paid enough attention to cement as an industry. We've never paid enough attention to get really, really good cement jobs. And that's another factor. But, you know, those I'm just pulling thoughts out of the air for. I can't prove those. I can show you illustrations of every one of those where it's a common practice or a common event. But, yeah, after that, we just need a lot more study on it. Any others? Yes.
I have a question relating to the toe. When you pickle, you put down an acid down there, does that alleviate any of the toe failures?
Pickling is not commonly done. You know, well, they'll put a little acid in front of a frac job, but it's more to break down with, because with a pickle, you need a certain amount of acid, a certain amount of surfactants to help you to suspend it, and a time period for that to react on. It's kind of like a reactor in that point. And then you got to get all that out of there, because if you push it into the formation, you're just pushing all that stuff into the perfs.
You're pushing trash cans.
Yeah. And pickling is an art. It just, some people do it well and some people don't. People that don't just say it doesn't work and they get away from it rather than learn actually how to do it.
Gotcha.
Yeah. Okay.
All right.
Hope you enjoyed it.
Yeah, thanks.
By the way, way, the reason I did this, I took my wife up to visit her two sisters and the multiple nieces and nephews up there. This enabled me to get out of the house for a whole day.
Token of our appreciation. Thank you.
Thank you very much.
Yeah.
Thank y'all.